for having me here at talking a bit about our um, experience with Rust. So what we did in a completely, not completely, but a bit different stage. Instead of doing embedded stuff, we are doing operating system stuff. And why do we do what we do? It's pretty much that we looked at the operating systems we have today, right? And we figured out that what we have were pretty much designed more than 30 years ago. The PCs are showing here is a x86, and that was the beginning of the 90s, pretty much, end of the 80s, where these devices came out. And what you had there at the time, you had desktop machine and not a lot of memory, and probably if you compare it now to some microcontroller, that is much less performance you had these days. And today this environment changed completely, right? So we have mobile phones, we have batteries, we have multi-cores, we are always online, we're on the internet, we have a high-speed network connection, and so on. So the environment where these operating systems were started looked completely different. And the second thing what we figured out is that our operating systems are really complex, right? So if you look at the lines of code, if you look how long it takes to build it and so on, there's a lot to improve. And finally, they are much slower than what's needed. So we believe that it's time to rethink the OS, time to think how it looks like. And this gives us the opportunities to fix the architecture, right? So if you start from building a new OS, then we can pretty much do everything what you want to like, and we can modernize the APIs, so we don't have to go back to what was right in the 70s when Unix was defined, or we don't have to do the very same APIs the people did in the 80s. We can do APIs now in the 21st century. We can get rid of a lot of legacy functionality, right? So you don't need to support DOS mode anymore, or you don't have to support all system calls, which are pretty much obsolete, but they're still in there because there's all software running. And finally, we can refresh the user interfaces, starting from the APIs to the to the shell, to the graphical user interface, up to how we build applications and so on. So there's a lot of things you can do if you rethink the OS. So therefore, a year ago, we started the Encourage OS project, and we started from scratch. So we simply said, we don't want to improve on existing systems. We started with a blank sheet. And the main goal of this project is to reduce the complexity, right? Because if you can do that, if you can build system much more simpler than we have today, then our secondary goals, like scaling to modern hardware, having less overheads, improving the security and the real-time properties, and so on, are much easier to achieve. Right? Instead of having millions codes of line where you have to add new functionality, we can make it much more simpler and less complex. So the question we had as we started the project was pretty much which programming language to use, right? And for us, a year ago, it was a little bit a tough question because we didn't know what we know now. Today, you have the latest answers. You just could believe Mark Rusinoff, which is CTO of Microsoft Azure, which said it's time to halt starting any new project in C and C++, and instead use Rust. Or you could just believe Reiner, which said in his last Heise talk that Rust is very good as a secure alternative to C, and it's nice for system near programming. But a year ago, we didn't know that. My prior experience was that I had written OS code in C, C++, and assembler for a few years, and actually for nearly 2 decades. And I even coded in dozen other languages. For my PhD, I even invented my own minimal system programming language. But I didn't have any prior Rust experience, and the similar thing with my team. So what we did to decide on language, we did a simple language contest. We figured out, okay, what are the strengths of the different languages? And for Rust, it was quite obvious, right? So you have many modern features. You have threads, you have closures, you have enums, and you have one killer feature pretty much, and that's memory safety. And that's one which you pretty much don't have in any other language for systems programming. On the other hand, for building an operating system, it needs to support low-level code, which was nice, which was available. And finally, if I have to sum it up in a single sentence, I would at that time I said that the language is richer than C and much nicer than C++. On the other hand, it's not only the language which counts, it's also the environment. And for us, there were many tools, or still many tools like Cargo, Raster, Grasformat, and Grades.io for the packages and so on. So that the environment was also a deciding point. And what we were surprised to see was two features, which is testing and cross-compilation. That was really easy. I still remember the days where you had to cross-compile GCC 2.9 something, and it took you a week to do that. And nowadays you just do a Rust up and you install the tool. And finally, there was a nice community, and we get 90 updates, so it's nothing like you have to wait for years for getting a new compiler version or something like that. So what I want to talk about in this in the remaining part of this talk is pretty much I want to reflect a bit on the lessons learned. So what have we learned from this experience of starting without any prior experiences and building an operating system? And probably looking at what are the missing features, right? So Rust isn't still perfect. It's getting better, but there's still a few features where I would say, okay, this will be improved in the future. So let's start with the modern features. So first of all, there's a learning curve. So if you start programming Rust, the Rust code looks like C, right? You do the very same thing you would do in C. You do the very same APIs. You do the very same static variables and all kinds of stuff. And what you do then, you gradually adopting more and more Rust features. As you learn more things, your code gets much better. Which means you have to rewrite existing code. You can't just program it and forget it. After a few months, you have to look back and say, okay, this I can do much better. And it's quite nice if you look at the, or explain this, if you look at the traits as abstraction layer. If you start, you use it just as for using existing APIs. So you implement something like core format, right? And you have these kind of features there. In the next step, you try to use traits for reusing codes across structs. So we have a trait called MMIO access, which allows our drivers to have the very same boilerplate code for accessing MMIO registers to be shared between them. In the third step, you're making your structs compatible. So they have a drop-in replacement of the same class of drivers. So you have an interface for UARTs, which are different drivers for, and if you use one, then you can pretty much use all of them at the same place. And finally, what we figured out is that we can use traits for unifying code across architectures. So we have a paging implementation, which is abstracted away the definition of the page table format, and it gets a unique interface for all architectures. So pretty much you start simple and you gradually increasing your knowledge of the system and making more complex use of the features. So there are a lot of features in the language, which gives you simpler code. So most notably are the iterators, which makes the code really clean and allows you to use operations with them. Like you can map, you can have a position inside them and filter stuff and so on. And it's actually mandatory because in the beginning we don't have any heap, right? So we can't simply allocate dynamic memory. If you want to process entries in a list or something like that, and they are converted on the fly, then the iterator is the right abstraction to use. Similar things like closures, which are really nice because they can really shorten your code. And if it's something that you have pretty much you do want to reuse or having a callback, something like that, then the closure is the right thing to do. Similar thing with error handling. The option the result is really nice that you have this question mark operator. It shortcuts all the error checking, and it makes this nested kind of stuff where you're calling a function, you have to look for the error code and then give it for the next layer of calls and then check for the error code again. It makes it really nice and clean if you know which types are. Maybe you have some idea on the similar type at least. And finally, there's this drop trade, which is really nice in an operating system because you can be sure that if something goes wrong, your resources are freed. So if you look, for instance, in the Linux code, then you have sometimes these go-to statements at the end of the function. If something goes wrong, then I have to make sure which of the initialization already happened. And if it has happened, I have to jump to the right place and then have to free all the resources, which is really ugly code because it's not maintainable. And if you forgot something, then pretty much you leak resources. With the drop trade, this kind of code is pretty much gone. Now, what about the memory safety, right? So the first step is the slices. They're really helpful because you don't have to check the length. It's done automatically. And on the other hand, it reduces the number of parameters to a function, which is a small benefit you have there. The borrow checker is a little bit more difficult. So learning the rules, learning how to cope with them takes time. So it's nothing you can do in a few hours. But what you feel after a year pretty much is that in the beginning you start to design around it, and you make sure that the borrow checker doesn't kill your code, and the compiler doesn't complain. You try to work around it, but later you start to design with it, saying, okay, if I have the borrow checker, how can I make sure that the things are used only once on these kind of stuff? So what are the limits? Well, we're building an operating system, so we are low level, so we can pretty much do everything we want with the CPU. This means we can actually break the memory safety inside the kernel, inside the hypervisor, inside this low level code. So it's actually breakable with unsafe code, and if you go for undefined behavior, that's easily possible to actually have this kind of bugs. So for instance, we once forgot to save some register in the kernel entry code, and it turned out to work quite nice in release mode, but it turned out that the compiler was using a different register allocation in debug mode, and then it crashed. And similar thing with inline assembler. You forget one register clubber and everything is, well, depending how the compiler behaves. So you can easily trash your whole program. Similar thing, if you do low-level coding, an operating system, you have to be careful on the cache maintenance instructions. If you leave something in your cache, then it could go really wrong on these old ARM CPUs. And finally, we had some bugs in the paging code. Well, which everything was right except that there was a different page into TLB. So this also breaks your assumptions that everything is memory safe. So our solution for that is that we want to minimize unsafe code, and that we test the code we have, which we know is security critical. We test it rigorously. So what about assembly? So assembly is pretty much the difference between, at least from a coding point of view, between the kernel and the application, right? So you need assembly. You need assembly to access special CPU state. You need assembly to access the CPU registers and for all these low-level things. You need it in the kernel entry path, right? If you have a system call, you need to save the registers. You need to context switch the CPU and so on. And we also use assembly to execute in controlled environment. If you want to fetch exceptions that happen, for instance, if you copy memory from kernel to user and back, then we have to make sure that the mem copy operation is touching only the registers we wanted, that we can recover from any page fault or from any exception. In Rust, we have these assembly macro, ASM macro, which is from a C programmer similar to ASM volatile and GCC. What we figured out is that naked functions are very important for us because they allow us to structure our assembly code, not only the small snippets you have for accessing a few registers, but the kernel entry code and the initialization code and this kind of stuff. Gives you a much better structure, and it allows you to document actually a large chunk of this code, which is otherwise really hard to maintain if you have hundreds of lines of assembly instructions just underneath. And the final stuff what the assembly macro allows, which I've not seen in another language yet, is that allows us to externalize constant parameters, which is really nice because then your assembly code can be parameterized. And we can show you this in an example. This is a simple function, not complete, but complete enough to explain that. How you would enable paging on x86. So this is a named function you see here. This gives you the ability to don't have a preload and epiload on the function. But it also requires that there's a single ASM macro statement inside it, and this macro statement has to be no return. So you can't return from that. Or it can't leave the return statement. You have to do the return on your own. And in this case, what we define is we define a parameter called set00, and we assign it a constant function called set00. And we simply use it by putting the braces inside the name of the constant. And the constant function we can document, we can calculate something. If you say you want to put in the last digits of p, you can simply calculate something like that if you can express it in a constant function. And you don't have these magic constants somewhere in your assembly code, which after a while nobody knows anymore why it is bit number 16 is set, right? So it makes the code really readable and maintainable in the end. There are also some limits, and I show you here on an interrupt table you could have on an x86 processor. On one hand, it shows you this .byte OX50, which pretty much is machine code, because what we want to use is we want to reuse this function for 32-bit and 64-bit. But in that case, we need two different instructions because the register names are different. If you put it just in push EAX, you will end up with a different instruction, and it wouldn't work. So what you can do is you can always go back to machine code pretty much. So that's one thing we learned here. And that's a missing feature pretty much, that you can't unify in that case register names, and in ARM you can't unify the instruction names on the inline assembly level. So sharing code between otherwise very similar encodings is not possible today. Another thing what you see here, and which was really old style assembly programming, is that the dot wrapped, dot set, and so on, and dot endr. These are pieces of macros inside assembly. This is something you would be familiar with if you look at how all the operating systems in the end of the 80s were written in pure assembly often, and then you have these macros inside, and then you have pretty much loops in the macro. And that's what pretty much the shortest way to express repeated insertion of assembly functions there. And so there are two things to learn here. The first thing is we didn't find a better way for repeating assembly instructions. So that's some basic feature. On the other hand, you can always go back to low-level stuff you already know from C or previous OS development. So you can still reuse stuff, and that's the nice property of the system. You don't have to do Rust specific stuff if it's not available. There is a fallback. So that was about the language, and now I want to talk a little bit about testing, because testing is really important for us, because we are building the code on our own. So we are humans, we make bugs, and finding these bugs early is less costly in the end, right? You don't want to produce 10,000 lines of code without any tests. So this is something which we can do with Rust much easier than we did before. And finally, we test because we support multiple architectures quite early in the project. So we decided that if we're building not only on ARM, not only on x86, but on different architectures at the same time, we can make the interfaces right. So we are forced to develop interfaces that unify all these architectures. And that's not possible if you have a small team, because usually the people tend to develop only on a single architecture, and the other architectures are getting outdated really fast. But if you have tests in place, if you can automatically test stuff, then that's actually possible. So for automation, we have simply GitHub runners. It runs dozens of cargo test jobs, which takes a few minutes, but it can be completely parallelized. So we can have multiple of them. And it allows us to run tests on every system level. So not only for the kernel, not only for the applications, not only for something unit tests or so, but on all levels. We can have different kinds of tests. And finally, it produces the documentation for us and some coverage reports, so we can make sure how far we are in our test efforts. So what are the limits of this testing? Well, one limit is that normal unit tests, that's what you do with cargo tests, only work on the host. So they are compiled for the host system, they run on your host system, and everything is fine normally. But if you do targeting multiple architectures, then probably just testing for x86, 64, the data structures is probably not sufficient. And on the other hand, it misses all this architecture-specific code, right? So usually to distinguish between x86 code and, say, in that case, ARM64 code, you do some config options, you do some barrier or guard here. And if you just do unit tests there, all this code is ignored. And finally, it misses the differences between 32-bit and 64-bit. So what we did is pretty much we figured out that, okay, we actually can run inside our unit tests inside a cross-compiled Linux environment. So you can specify the target for the cargo test, and you can pretty much have a cross-compiled installed Rust toolchain, and it compiles the code for a Linux environment. To do that, you have to install, of course, the Rust compiler. You have to install a special linker because normally it uses GCC for linking, and that's not available. And you have to specify a special environment variable so that this linker is used. But the trick is not, on the one hand, not on the compiling, but more on the how you execute that stuff. Because now you have an ARM64 binary, what you do with that. And there's a nice thing which is called QEMU user bin format, which allows you to transparently execute these binaries on top of your x86 machine, right? So it executes the binaries, and all system calls done by these binaries are translated to the host system. So that's really nice because you don't have to provide any additional script, boot up a virtual machine, or this kind of stuff. The QEMU user bin format does it for you. So now we have cross-compiled unit tests, which is quite really nice, and it also found a few bugs. Another feature we have are integration tests, which are really easy if you use custom test frameworks, which is a feature of Rust. And so you annotate your test functions with test case, and you can run them for any layer. We can use it on the user level, on the application level. We can use it in the kernel and in our hypervisor. And what we do there is we execute a lot of test cases. In the end, we report an error code. And we do it inside QEMU, so we have to get the error code out. And there is an easy part, which is on ARM. We have semi-hosting, a feature which allows you to pretty much return the exit code to the host. And on x86, you have something called debug port, a feature of QEMU, which allows you the same thing. With this integration test, with this custom test frameworks, we found a lot of bugs. So, for instance, we found out that we initialized the CPU not correctly, so the kernel were able to override read-only user memory. So now we have a test in place that you boot the kernel and he tries to access user memory, and it should be a page fault. And you catch the page fault, and if the page fault is catched, then the test succeeds. Similarly, we forgot an initialization of some kernel data structure, so we can now test whether the data structure is correctly initialized. We figured out that there were some system call bindings out of sync, so we changed the kernel, added the system call, but in the user level, we forgot to do that. So this is the kind of tests you can find. And finally, we find some performance bugs. So we had some assumptions, how long instructions would take, how long a certain implementation would lead us to, and we wrote a test, run it inside the kernel, and figured out, oops, this was the wrong decision here. So you can find a lot of bugs with this kind of integration tests. And the final thing I want to talk about is about the coverage, right? So if you do tests, you never know how good your tests are. And so that's why we figured out, okay, we want to do measurements on the coverage. The problem is that the existing tools were not able to work on all targets, right? So they were mostly for x86, there were a few ones for ARM, but what we wanted to have is we wanted to have one coverage for all our architectures. So we figured out that LLVM source-based code coverage is the right approach for us, because the compiler directly inserts the profiling counters and it just works. The problem is the profiling runtime of LLVM is really bad for these kind of no standard environments. We don't have an allocator, because the interface says something like, okay, if you want to write out these profiling files, then you need to allocate this big chunk of memory, because otherwise I can't give you the data. And finally, the question was, well, how can we get the data out of QEMU, right? How do we communicate from inside the kernel in QEMU, where we get this information down to the host system? And what we did to solve that is pretty much we built our own profiling library. So the hardest part was there to reverse engineer the raw file format, because there's no really good description. There's some bad, I would say, C code of that. And you have to figure out what all this thing means. And the good thing about it is that all data is already available in the ELF file you're starting, and you can write it actually incrementally. So it's a bug on the profiling library interface that it doesn't allow you that. So you don't need allocation. You can do it. You can do it pretty much on your own, step by step, writing out all the profiling counters and the definition of the functions and all that kind of stuff. The padding was really strange, and it turned out that they pretty much assumed a certain padding and C code that it would work. So they never really thought about padding. It's just a raw dump of the data structures they had in C, in the C lab. So for communicating to the host on ARM, it's relatively simple. Semi-hosting allows you to write files, which is a little bit dangerous because you can overwrite files from the testing environment in the host. But it gets you the data out pretty much. x86, it's much easier to pipe the stuff through a second serial port, which is a little bit more complicated on ARM, but would also be an option. So in the end, what we can do is we can measure coverage on all our architectures, merge them together, and get a nice report of saying you have X% of your code coverage. So what are the conclusions for me after choosing Rust a year ago, pretty much? From one point, it was a risky decision, right? So we didn't have any experience. We don't know what it would turn out, but in the end, we figured out that was the right approach, because for our goal, reducing the complexity of the code, and modern language is exactly what we need. So we couldn't have achieved the same with the same effort if we would have stayed with C. And on the other hand, we figured out that good tooling is really important. And that was one point where I decided, okay, if we stayed with a different programming language, even the one I developed, we would never have these kind of tooling we got with Rust. And the second last point is that we are doing all the stuff on the nightly release of the Rust toolchain, which is really nice because it allows us to keep up with the Rust changes. So pretty much every 1 or 2 weeks, there is a Clippy update, and we can just fix our code, and it's automatically reported by our tests, and it's easy to make sure that the code always compiles. There's also this option that if you want to go back to previous releases, there's always this option to check out or to switch to an older version of the nightly compiler, so we can still compile something which is a year old. But finally, it's still early in the learning Rust, so there's still things to just say, oops, that's interesting. We could use that, there's still features we are exploring. And we'll see how this conclusion would look like, say, in a year from now. If I want to try an outlook, then I would say your next OS will be written in Rust. So there's a path. If you are a Rust developer, there's a path if you start from C to go to Rust. But I found out that there's no way back. If you have programmed a time in Rust, then you don't want to go back. It's not a good idea to get or to drop these nice features we have now and to go for something on a much lower level. So this means, if you think this through, then this means that existing OSs will be rewritten completely, or if they're not rewritten, they will be abandoned in the end. So that's basically for me.